Greetings! We have finished learning all of our factoring techniques, but a question I often get is, what factoring technique should I use and how do I know? So let's try to put it all together and make sense of which factoring technique sometimes makes the most sense compared to others. So I've created this chart here that contains all of the different factoring techniques that we've learned. The very first thing we look for is if there's a greatest common factor. So we ask, is there a GCF first? That's the very first thing that we do. Then we identify, well, how many terms do we have? Could I possibly use a special factoring technique if I have a difference of perfect squares? Or perhaps if I have 3 terms, is it a perfect square trinomial? If not, what does it look like? Is there a number in front of x squared? Is there not a number in front of x squared? And then finally, we learned 4 terms, we use grouping. So if we do all of those things and nothing works out and nothing can happen, then our original expression is what we call prime, unfactorable. And we always want to make sure that we can, if we can factor further, to do so. So we always want to check to see if we can't go one step further in our factoring techniques. So let's factor completely 5x squared minus 32x minus 21. So I'm going to pull up my chart here off to the top right hand side. You'll see that I have the 5x squared minus 32x minus 21. Does this have a GCF? Well, they're not all divisible by 5 or 2 or 7 or 3 or any of the other factors of 5, 32, and 21. And I notice that they all do not have an x, so we don't have a GCF here. I see I have 3 terms. It's not a perfect square trinomial since I cannot rewrite my first or my last term as a perfect square. So then I need to move into my middle column here. I notice that I have 5 in front of my x squared. So I'm going to need to use the AC method by multiplying 5 times negative 21 and splitting my middle term. Let's tackle that. We need to multiply 5 times negative 21 to reach negative 105 and then add to negative 32. I see that's negative 35 times 3 gives me negative 105. And if I were to add negative 35 plus 3, I certainly get negative 32. Our next step is to rewrite our middle term. That's why it's called the AC split method, using those perfect numbers that we found. So this will give me 5x squared minus 35x plus 3x minus 21. So I just split our middle term there. Now I have 4 terms. We know with 4 terms that we factor using grouping. So I'm going to group my first 2 terms and my second 2 terms together. I notice that my first 2 terms are divisible by 5x. So when I divide 5x squared minus 35x, I end up with x minus 7. When I look on my right-hand side, I see they're both equally divisible by 3. So when I divide them by 3, I get x minus 7. I now see I have a common binomial. I can divide each side then by the common binomial, and my leftovers are 5x plus 3. We can always multiply through using FOIL or distribution in order to check our answer. Let's say I have a cubed plus a squared b plus ab squared plus b cubed. Is there a greatest common factor? So I don't see they all have an A, and I don't see they all have a B, so therefore there's no GCF. We do see that there are 4 terms. So when there are 4 terms, we will use factoring by grouping. So I'll group the first 2 and my second 2 together. I notice that my first 2 are divisible by a squared, leaving me with a plus b. My second 2 are divisible by b squared, leaving me also with a plus b. I see they share the common binomial of a plus b, and a squared plus b squared is left over. I notice that I have something squared plus something else squared on the right, and although you may want to use the difference of perfect squares here, note that the difference of perfect squares requires that we have subtraction and not addition. So at this point, we're done. Let's tackle x to the 4th minus 81. Is there a greatest common factor? No, I do not see that they're both divisible by the same number and or letter. I see that there are only two terms. When I have two terms, our only option is to use the difference of perfect squares. So here's our difference of perfect squares rule. Can I rewrite my first term as something squared minus the second term as something else squared? Well, I see that I can rewrite x to the fourth as x squared squared, since 2 times 2 is 4 when we have a power to a power, minus 81 can be written as 9 squared. So I was just able to write something squared minus something else squared. So its factored form is to add those two somethings together and subtract those two somethings together, giving me x squared minus 9 and x squared plus 9. I also see that I may have another difference of perfect squares and can factor one step further, since I can rewrite x squared as x squared and 9 as 3 squared. So I have another difference of perfect squares, giving me on the left-hand side x plus 3, x minus 3, and then bringing down the x squared plus 9. We cannot do the difference of perfect squares on the right-hand side because that has the addition of perfect squares, and our rule simply states the difference. 12x cubed y squared minus 38x squared y cubed plus 16xy to the fourth. Is there a GCF? Yes, of course. They're all divisible by 2xy squared, so we'll take care of that part first. If I divide them all by 2xy squared, that leaves me with 6x squared minus 19xy plus 8y squared. Let's see if we can continue factoring. 6 and 8 are not perfect squares, so the perfect square trinomial does not work. I see there is a number in front of x squared, so we're going to need to use the AC split method. So we'll need to take and find two numbers which multiply to 6 times 8, or 48, and yet add to negative 19, the middle number. I see that negative 16 and negative 3 work perfect. So because we had to multiply the first and the last, we need to split our middle term using these numbers. If I split my middle term, I end up with 6x squared minus 16xy minus 3xy plus 8y squared. I'll come back to that 2xy squared in a moment. I'm just going to continue factoring, but we'll come back to that, so I didn't forget about it. Because I have 4 terms, now I'm going to group the first two and the second two together. I see the first two terms are divisible by 2x, so when I divide my first two terms by 2x, I end up with 3x minus 8y. Now I'm going to look at my second two. I don't see that they're divisible by a number, but they are divisible by negative y. And I'm going to divide them by negative y such that my signs change so that they match the left-hand binomial. When I divide by negative y, I end up with 3x minus 8y. So I see I have the common binomial of 3x minus 8y, and my leftovers are 2x minus y. But again, I did not forget we need to bring down that greatest common factor that we first took out, giving me 2xy squared times 3x minus 8y times 2x minus y. Let's try 2r s to the fourth t minus 9r cubed s to the eighth t. Is there a GCF? Well, I see they share some r's and some s's and some t's. Particularly, they share 1 r, 4 s's, and 1 t. So when I factor that out, I end up with 2 minus 9r squared s to the fourth. Now, I do have two terms, and we are in subtraction. However, 2 cannot be written as a perfect square. So this may not follow the difference of perfect square rule, since 2 cannot be written as a perfect square. So even though all we had was a greatest common factor, we still factored, and this is complete. So our answer is the r s to the fourth t times 2 minus 9r squared s to the fourth. P to the fourth minus 10p squared plus 9. Is there a GCF? I don't see they're all divisible by p, so I don't think so. I see we have 3 terms, and I notice that the first and the last terms are perfect squares. Perhaps we could use the difference of the perfect square trinomials. Since p squared, or p to the fourth, can be written as p squared squared, and 9 is the same as 3 squared. So here's our rule. I see that I have the second piece here with the subtraction that matches the subtraction here. But if we need to use this rule, we have to check our middle term first. So is 2 times p squared times 3, oh my, that equals 6p squared, not 10p squared. This rule's not going to work. This does not fit our perfect square rule, so we'll need to try a different technique. Because there's nothing in front of p to the fourth, I'm going to see if I can't find something which multiplies to 9 and adds to -10. So -9 and -1. I can write it in its factored form by jumping to its factored form because there's nothing in front of p to the fourth. This gives me p squared minus 9 and p squared minus 1. And if I were to FOIL, I would get p squared times p squared, which gives me p to the fourth. If I were to continue FOILing, I would end up with our p squared in the middle. But I see that I have p squared minus 9 and p squared minus 1. And I can rewrite all of those using perfect squares. So I can rewrite p squared using p squared, and 9 as 3 squared, and 1 as 1 squared. And they're both in subtraction, which means that I can use the difference of perfect squares rule. So that p squared minus 9 is the same as p plus 3 and p minus 3. And p squared minus 1 is the same as p plus 1, p minus 1. So we see that sometimes we can use more than one factoring technique during a problem when we're trying to factor completely, always trying to look for one step further if possible. Now, it's not always possible to go one step further, so don't try to force additional factoring techniques when they're not there. And remember, we can always multiply, distribute to check our work to make sure that we factored correctly. Next time, now that we know how to factor using all of our techniques, next time we'll chat about solving using factoring.